Hooke's law and its experimental verification. Hooke's law. Hooke's law states that within elastic limit, strain is directly proportional to stress. Mathematically, sigma proportional to epsilon. Stress proportional to strain. Here you have the experimental apparatus. Experimental verification. A thin wire of length L and a cross-sectional area A is suspended from a fixed point. Here you have this wire which has a length L and area of cross-section A. After loading the pan, the pointer stands at 4. A pan and a pointer are attached to the free end of the wire. When we add 50 gram, the wire gets stretched. When we add one more 50 gram, the wire gets stretched further. Let us add one more 50 gram, the wire gets stretched. The elongation is more when the load is more. 4 is the initial length and 4.8 is the final length. The elongation is 0.8 centimeter. When weights are added, the wire stretches and the elongation del L is measured using a vernier scale. The elongation del L is directly proportional to the original length L. More is the length, more will be the elongation. Then, the elongation del L is inversely proportional to the area of cross-section A. If we take a thicker wire, then the elongation will be less for a given load. We are taking the stretching force along the x-axis and the extension del L along the y-axis. The origin is O. We get a straight line passing through the origin. A graph of force F versus elongation del L is a straight line passing through the origin. Instead of del y, let us consider here del L. Instead of del x, let us consider del F. So the slope M equals del y by del x, but here it is del L by del F. Therefore, slope multiplies del F equals del L. Let us multiply the numerator and denominator on the right hand side by AL. Now, let us rearrange. We get del F upon A equals L upon A times slope. This is a constant quantity, multiplies del L by L. So, del F upon A proportional to del L by L. Del F upon A is called the stress, whereas del L upon L is called strain. Therefore, sigma proportional to epsilon. That is, the stress is proportional to the strain in the elastic limit. Stress-strain curve. Along the x-axis, let us take the strain, and along the y-axis, let us take the stress. The cut is the origin. We get a curve. Up to A, we get a straight line. Then the line slant along towards the strain curve. After that, we get different points A, B, C, D, E. So we get OA one portion, AB is the another portion, BC is the next portion, CD is the other, and D is the final portion. Let us learn each part. The strain is on the x-axis, whereas the stress is on the y-axis. The stress-strain curve is a graph that shows how stress and strain changes with each load. This graph helps analyze the elastic property of the materials. Here, let us consider the portion OA. It is the elastic region where the stress is proportional to strain. So Hooke's law applies here. The point A is called the limit of proportionality. Beyond this point, Hooke's law is not valid. Let us go for the next portion AB. Portion AB. Strain occurs more for a given stress. Hooke's law is not valid here. When force is removed, the wire returns to its original length. So, the curve follows back its own path, finally it reaches the origin O. Point B is yield point, that is the elastic limit. Beyond this, the wire does not fully recover. Elastic behavior shown by the portion OAB in the stress strain curve. Let us now consider the next portion BC. Portion BC. This occurs when the wire is stretched beyond the point B, beyond the elastic limit. The wire does not return to its original length after removing the force. Suppose, let us consider a point between B and C. Then we remove the stress completely or step by step. Then we get a line that will not retrace its path but go in a new path and reaches X. The OX is the permanent set. The wire does not return to its original length after removing the force. This marks the beginning of permanent deformation. Let us go for the next portion CD. Stress increases, causing strain to rise quickly until a point D. For a less stress, we get more strain after C. Beyond the point D, even if the load is removed, strain keeps increasing, leading to breakage at a point E. Point D, this is called fracture point. Breaking stress or tensile strength is the maximum stress beyond which the wire breaks. The point D is the fracture point. Breaking stress is the maximum stress beyond which the wire breaks. The region BCDE represents the plastic behavior of the wire where permanent deformation occurs.